Polar conic sections.
Yeah, so we've dealt with these different types of conic sections, and now we're going to talk about how they exist in the polary fashion. And,
Right. Did you say polary?
Polary.
Okay.
Okay, so this is, you'll have to remember back when we did this, we did R equals,
a lot
and then
of
we
moons
had
ago.
stuff, and then like a theta.
Right.
So we had these points R comma theta versus X comma Y,
Right,
which
and
is
remember,
a Cartesian.
R was your radius and theta is the angle that you've moved.
Exactly. So we still basically have the same idea. A conic section is the set of all points on a plane whose distances from a particular point, which we call the focus, and a particular line, the directrix, in the plane have a constant ratio. Now, I believe the only one of these we actually talked about a directrix with was the parabola, but
Right.
we actually can talk about having a directrix
With all of them.
With all of them.
Yeah, and here's the cool thing. Polar coordinates actually make it easier to write some of these conic sections, honestly.
Yeah, they do. They do. And you'll notice here, like, what would you say this is a graph of?
You know, if that's all I see, I would make two guesses, but mostly because I'm a teacher.
Yeah, okay.
I would say it could either be an ellipse, you know, it could be a parabola, or maybe a hyperbola. I don't know.
Right, and
I mean, it could be all three.
That's the thing. If this is all we're given, like the graph could continue on, and we could have an ellipse, we could have a parabola, we could have a hyperbola. And so when you look at the bottom of the page at those examples of graphs, realize that these could be any of those
They could be any
types of
graphs.
graphs.
We have to do a little bit more math to determine exactly which one we're working with.
Right. And so what we'll have is a focal axis. That's the axis that goes through the focus and the vertices. And then we've got the directrix, which is a line that's perpendicular. And what happens is at any place we want to pick on the conic section, the distance from the focus to the directrix is the same.
I mean, that's what it looks like. So.
It looks like. Or has the same difference or something like that. A parabola has one focus and one directrix. Ellipses and hyperbolas have two focus directrix
Which
pairs,
makes sense.
one on each side. So we could set up like another side over here for our ellipse and have another vertex and
just
focus
depending on the information we were given. Yeah.
All right, so let's look at the next part of the notes real quick. So here's our relationship that we've got. There's a special relationship.
Special.
With focus.
They're engaged.
Yeah, you might say. Oh, you might say focus directrix eccentricity relationship.
So here comes that guy again. So it's important now with polars because we have to actually use the eccentricity to help us determine which type of conic section we're using.
Absolutely. And so we had the formula in our packet things that was like E equals C over A.
Mm-hmm.
Well, we're gonna, because we may not know C and A the way these are set up, we might know, and we actually, there probably aren't any problems like this, but basically the idea, if you look at that picture up top, is that from P to F over P to D, that ratio is what E is.
Right.
So that's kind of interesting.
Right.
From the eccentricity, we can tell if it's a hyperbola, a parabola, or an ellipse based on whether it's equal to 1, greater than 1, or less than 1.
Right, so now this is going to be where the eccentricity is a little bit different than when we were in Cartesian form, because when we said you had an eccentricity of 1, you had a circle, and that's not true now.
Right.
Right. Add
Graphic organizer.
Is that not on the
No,
is that
it's
not
not
on
on there.
Oh.
So you might want to add those inequalities to your graphic organizer.
And put it on the very back page where you put your conic section
where we've
stuff.
got the other conic section stuff, right? So that you should have these pictures there. And so, like we said, any of these could be a parabola or a
ellipse
whatever.
or hyperbola. Yes.
And so they look kind of scary maybe, but they're really not that
They're
bad.
totally doable.
And the thing is that what matters here is where our directrix is. If our directrix is x equals k, we've got cosine and a plus sign here.
And that's an x equals a positive number here, not like an absolute value situation or anything like that. Like x needs to be...
Like you'll have like x equals 2.
Right.
Well, since that's a positive number for k, that's different than if we had x equals negative k. That would give us this equation, which is 1 minus e cosine theta. And if you remember that x's and cosines go together, then that might help.
Y's and sines go together, just like we learned way back in October.
But we don't have to have that memorized since we have these in our graphic organizer.
Hey, fabulous.
So let's just look at some examples real quick.
You know what? That's a great idea.
Okay, so given that the focus is at the pole, and pretty much all of these will be, but they had to say it.
Well, they'll have one focus at a pole.
Yeah, one focus is at the pole. Write a polar equation for the specified conic and graph it. So A, the eccentricity
Yep.
here, 3/5, that tells us that we have an ellipse. So, and it doesn't really ask us to specify, but let's just
need to know.
say
It helps
it's
us
a
sort
good idea.
everything out if we were to graph it.
Right. Now, the way we figure out which formula to use is based on the directrix. X equals 2 means you use A.
Because 2's positive, and it's an x equals situation.
Right. And that also tells us that K equals 2.
Right, because x equaled k.
Right. So we know that E is 3/5. We know that K is 2. So we're going to plug it into the formula in part A. So that's
2 times 3/5 over, and then 1 plus 3/5 cosine theta.
okay. Now there's a really easy way to simplify this up since we've got fractions.
Right.
And that is to multiply the top and the bottom by 5.
Right, and the reason you can multiply the top and bottom of a fraction by 5 is because you're actually, when you do it just like this, 5 over 5 reduces to 1. So all we're doing is multiplying our fraction by 1. We just chose a super specific one.
Right. And so what that does is on top, we're multiplying this, and think of it like it's 5 over 1, right?
Right.
So,
oh, that's a double fraction.
So we're going to take the 3/5 and times it by 5 over 1 because that cancels out our 5. And then that means we just have 2 times 3 on top, which is 6. That's over, on bottom here we have to distribute across the plus sign.
And multiply the whole thing. So
So-
it's not just times the 3/5 part, it's times that 1 in front as well.
Right, so 1 times 5 is 5, and then 3/5 times 5 over 1 is 3. And we're doing this because we don't want fractions on top of
Yeah,
fractions.
but fractions on top of fractions equals no bueno.
So this right here is our equation for A.
And see, that wasn't that bad.
No, that's
No,
not
it's
that
pretty-
bad. Now, if we want to graph it, you take your calculator,
Put it in polar mode.
put it in polar
and
mode
just type
and
that
radian.
guy. Yeah, you want in radians. 1 in radians.
Type it in. So
Just type
6
it in.
divided by open parentheses, unless
Or
you've
you
got
can-
that fraction
yep,
button.
use the fraction.
And then I would zoom square it because otherwise your ellipses
Yeah,
might look like
yeah, mine-
circles.
yeah, and
this
that's not-
actually looks like a circle.
It does look like a circle, but it isn't. It's an ellipse.
Well, it's kind of a circly square kind of situation. And you don't have to be
Did you
super
say a circly square?
Never mind. Forget that. You don't have to be super specific on these graphs, I would say. Would you say?
I
mean,
wouldn't say so. We need to be ballpark, but
Ballpark.
you know, like if you have an ellipse that's almost a circle, give me an ellipse that's almost in a circle, not one that looks like a racetrack.
What if the racetrack's a circle?
But racetracks are more stretched out.
Okay, so E equals 1.
Yeah.
So that means that we have a parabola.
Yeah, parabola. Parabola.
And then we know E is 1. We know that the directrix is actually equals
Negative
-2. So K again is 2.
But,
Not negative, because that
What?
negative, if you look, the directrix formula is X equals -K. So
Right.
K is positive 2. The
Oh,
negative is
gosh.
going to come in our formula. We've got R equals K times E over 1 minus E cosine.
oh, it already shows up
It
in our
already
formula.
shows the
Gotcha.
formula and it's got the minus.
Man, I was
This
starting
is
to
this is the ideal situation here because there's no fractions, so we just have to
No fractions equals amazing.
So we just have 2 over 1 minus cosine theta. So that's our formula. And then if I plug that into my graph, well, that was a close one. I almost didn't put parentheses.
Sorry, I had to check something. Hey, if you're gonna throw that around, just give it to me.
You want it?
I mean, hey, that's a parabola that opens east and west.
East and west? How can it open east and west?
Goodbye, Jordan and Rachel. Goodbye.
Okay.
Or don't leave.
Okay.
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 There you go.
There you
So
go.
part C, 3 halves.
So this must be
It's got to be a hyperbola, 'cause that's the only one we haven't done yet.
hyperbola.
Hyperbola.
Yeah. So K is positive 4.
Right.
And since Y equals
Now it's a y equals, so
4,
we're going to have a plus cosine, a plus sign situation. It's a positive 4, which means plus sign on the bottom.
So K times E, so 4 times 3 halves on top, and then on bottom
1 plus 3 halves sine theta, and then we're going to multiply by 2 over 2. And that cleans our problem up, and we're going to be super happy people.
Right.
Yeah.
All right.
Toad's happy.
So on top, it gets rid of this 2, so that I just have 4 times 3 on top, which is 12. And then I distribute the 2 on bottom, so that's 2 plus 3 sine theta.
There you go.
And then I plug it into my calculator.
And these actually graph a little bit differently, if I remember correctly.
They look kind of weird.
I haven't graphed one in a while, but
It
I feel like
definitely
it's a little bit-
has an issue with the asymptotes. Remember, we've got asymptotes on
Right.
hyperbolas.
yeah, it puts them in there,
And so
which is really fun.
my window's not quite savvy. I think I need to do more of a zoom standard situation. No, it
No,
needs to be
you're gonna
even
have
higher
to
than that.
to move up a little bit. So anyway, you would mess with the window on that to get that whole entire graph.
Of course.
Yeah.
Ain't nobody got time for that.
Ain't
So-
nobody got time for that. But it's going to be, and on most of the, at least on the 84 plus, the silvers, I don't think on the Inspires so much, it does put the asymptotes in there, which is good because that is, technically part of the graph of a hyperbola. It's what that's that
How does
bounding
my
factor.
hyperbola look?
That
Does
looks
that look good?
great.
Are you lying to me?
Why would I lie?
I don't know. Okay.
Okay.
Example 2. Determine the eccentricity, the type of conic, and the directrix. Now, this is gonna.
We're going reverse,
right,
basically.
because we want this to be 1 plus, and then we'll
Something.
have e
Right.
cosine theta.
Right.
And so, in order to get that, we need to divide everything by what?
By the number in front of the cosine.
Right.
I'm sorry,
No,
the number in
out
the very front. Yeah.
So we're going to divide everything
By
two.
2, everything.
The only way we can do that is if we divide everything by 2.
So this is basically the
We'll
same thing as multiplying the numerator and denominator
By a half.
Which again,
Jinx.
you owe me a soda.
No, you owe me a soda.
Ugh.
I said jinx.
Shoot.
Okay, anyway, so that gives
But again,
us
we're multiplying by 1, which makes the difference here. It makes it all legal,
mathematically.
mathematically legal. I mean,
Okay, so we know 2 things from this. We know that E is 3/2. And then we know that the top here, the top equals KE. And so we can plug in that 3/2 right here. There's an equals sign right there.
yeah, that needs to be equals.
And you can either be like, oh, I can think about this and know what this is, or multiply both sides by 2/3.
K has to be 2.
K has to be 2 because 2 times 3/2 gives you 3. So K equals 2. So E is 3/2. That means, since that's bigger than 1, that means we have a hyperbola.
Yep.
And then
K equals 2, so that's an x equals 2 situation
Because
we have
it's
cosine.
positive
It's a
cosine.
positive cosine. There's your directrix right there. Bam. That wasn't so bad.
no, it wasn't. So let's try it again.
Okay, now on this one, we're going to have a situation where we're going to have y equals a negative number
Because it's
for our
negative
directrix
sign,
because we have a
right?
negative sign.
And so
And we're going to divide by 4.
Yeah.
Or multiply the top and bottom by 1/4.
right. So that gives 6/4 on top, or 3/2, you might say.
3/2. You might say, you don't say.
You might,
Oh.
if you wanted to.
Okay.
All right, so that gives us 3/2 over 1 minus 3/4 sine theta, and then that
And
means that,
Eccentricity is 3/4.
which means
Then
this
we're going to
is
have k times 3/4.
K times E, so K times 3/4
And that's got
Equals
to equal 3/2.
3/2. And so what do we multiply that by?
4.
So you move this over by multiplying by 4 over 3. So that's 2, isn't it?
That's what I said. 2.
Okay, K equals 2.
K equals 2.
So E equals 3/4, K equals 2. If E is 3/4, that means we've got an ellipse.
Yep, ellipse. And y equals -2 is the directrix.
Right.
Right. Righto. Bam.
Example 3.
Example 3 indeed. Let's analyze and convert from that to Cartesian.
Let's. Okay, so to start this off, we're going to do like we did in example 2, where we write this so that we know what E is. That's going to be
Right.
our easiest thing to find on
Right.
this problem. So to do that, we divide by 5. Why? We need this to be a 1 to be like
Right.
a standard formula.
Yeah, just exactly how we ended off on the other slide. You're either dividing everything by 5 or multiplying the top and bottom by 1/5.
Whichever way you
So
wanna think
whatever
about
way is most comfortable for you.
All right, and that tells us
That is the nastiest theta I've ever seen.
That's okay. So that tells us that E is 3/5, which means this is an ellipse.
Right. Now, rewind just a little bit, if you will, back to our original study of ellipses, or flip your flippy chart.
Flippy chart, yeah?
And you'll notice that the eccentricity of an ellipse is C over A. Check that out. So we have A and C and E.
Now, there is a possibility that you could have something that's like a multiple of 3/5.
Like 6 over 10.
Right.
Right.
So we're going to assume it's the easiest
Simplest
case
version,
unless
yes.
we have some reason not to.
Right,
Okay.
right. And you can always, like when you're done, you could graph this and
check and make sure.
check and make sure.
So we're saying C is 3, A is 5, simply because we broke up our eccentricity this
Right.
way. And so that means that we
can find B.
We just need B. And if you look at your ellipse relation, that relation is A squared minus B squared, and that minus sign is important.
Pretty important.
So we do 5 squared minus
B squared
B squared
equals 3 squared.
So you subtract 3 squared over, add B squared over, and get 25 minus 9, which is 16. How convenient.
Man, that is so fortunate.
Square root, so B is 4. So we just found A,
So-
B, and C.
Yep.
Now,
and we found E.
and we found E, and we want to write it. It doesn't say, but let's go ahead and write this as a Cartesian equation. And to do that, the only thing we have left is the center point.
Right. So what I would do is I would just sketch out a real rough sketch of kind of what we've already discovered, just to get an idea of, hey, where should the center be?
Yeah, so why don't you tell me what we've
Well,
discovered?
here's what we've discovered. Number one, we know that we're only working with problems that have a focus at the pole. So we know that's true. We have
Okay,
one focus
that's our
at the
focus.
pole. Okay. Now, before we can figure out our center, we have to put our directrix on the graph so we get an idea of how our shape should look.
Right, because the center is the opposite direction of
Right,
the directrix.
of the directrix. Well, we're told that we have minus 3 cosine theta.
Mm-hmm.
Okay? The minus sign means that I'm going to move left.
So somewhere over here is
right,
our directrix.
and the cosine means I'm going to deal with an x equals situation.
Right, so that means our center point should be somewhere over
right,
here.
now, we know right where the center point should be because the distance from the center to the focus is 3.
So
And we know that because that's what C is. So that distance is 3. Which means that the center has to be at the point 3, 0.
and that's at either kind of point.
Yeah, it doesn't
Whichever
matter
way
if
you do
you're
it.
doesn't matter which one you're in.
Okay, so
Okay.
so it has to be at 3, 0 because we're not going up and down at
Right.
all. We just and if we wanted to continue drawing this out, then we would have
Just move 2 more units past the focus. Whoa.
to get this
to
would
get
be
to your-
5, so we'd
to
have
get to your
our ellipse
vertex.
that way, and
Right.
then we'd have 1, 2, 3, 4, 5 that
Right.
way. And so here is our ellipse.
Wow, that's
Not bad for
not bad.
considering.
That's not bad at all. So our equation then is not difficult to write either.
No, totes easy.
Totes jelly.
Ellipse has a plus sign in the middle, and
Right.
that's important.
Yes, it is.
I don't
Tres
need that.
importante.
Trace?
Yeah, very.
3 important?
Oh. Did I just mix up French and Spanish?
I don't know. I don't know at all.
All right, so we're going to find a polar equation for the ellipse with a focus at the pole
Okay.
and the given polar coordinates at the.
Okay, so
I
here's.
didn't even get to say the given polar coordinates.
You were in my way. Okay.
Okay, so let's graph this.
Let's draw a nice little sketch.
Let's draw a nice little sketch. Oh, if the OCD kids get a hold of that, it's going
not that
to
bad.
drive them crazy.
Okay, now 1 comma pi over 2. If we're graphing
So
this,
remember-
you go to pi over 2, which is up and down,
Right.
90 degrees, and then you go out 1.
1 unit only, okay?
So right here is one of our endpoints. Then we're going to go around to 3 pi over 2, and we're going to go out 3.
Now remember, we have a focus at the pole here.
And it tells us it's an ellipse, by the way.
So we know a couple things that we should be shooting for right off the bat. Number one, our eccentricity needs to reduce and be less than 1. So if we do our math and we get an eccentricity larger than 1, we've got an oops.
Yeah. The other thing is that the endpoint that's closer to 0, 0, if we can draw a directrix on that side and then look at on our thing to see which of these equations we should use.
Yeah, this is going to be a plus sign situation.
Yeah, this looks like C. So that means we are filling in this right here. And here's what we can do. We can actually use these 2 points because these 2 points are our r's and thetas.
Yeah, hey,
and we can make like a system of equations. And it'll be totes easy.
Why can't you just count?
Count what? How do we count K and E?
Well, don't we need like C and A? So if I know where the center of my ellipse is, I can get C and A, right? I can at least get A.
Okay.
Well, you keep going.
Okay. So sine of pi over 2 is 1.
Right.
So this will end up being 1.
Right.
So that we have 1 equals KE over 1 plus E. If we multiply both sides by 1 plus E to get it off the bottom, we get 1 plus E equals KE. Now let's work with the second point. 3 equals KE over 1 plus
Now, remember, Mrs.
sine.
Stevenson's working in polar coordinates here, so we're saying that this equation, this R equation, has to equal these points, and we're saying that because we graphed it to get an idea of where it's located, where the directrix is, and all of that kind of stuff. So we're actually using points we know for a fact given to us in the problem. Which sometimes can be hard to remember.
Right. Sine of 3 pi over 2 is -1, so we really have 1 minus E happening here on the bottom. We multiply that over, and we have 3 times 1 minus E equals KE.
Hey, KE's equal the same thing.
Right, so we could group them up and set them equal to each other. So 1 plus E equals, let's go and distribute.
Let's do it, 3 minus 3E.
Minus 3E. Get your E's together. 4E equals 4.
Did you say
What?
get your E's together?
So E equals 1. I thought that. How does E equal?
E can't equal 1. That's a parabola.
Oh, 2, right? I would wait, I added 3E to this side and got 4E, so I subtract 1 to that side.
Yeah, okay, there you go. All
My
right.
bad. That's why you shouldn't do math so fast. I'm just kidding. Okay, E equals 1/2. Okay, so E equals 1/2.
And we used our knowledge of eccentricity to figure out there was a mistake there,
Yeah.
by the way.
Yeah, we did. And then you can plug that back in wherever to find K, somewhere up here.
Doesn't matter.
Okay,
Just pick one.
so like this right here. So 1 plus 1/2 equals K times 1/2.
Right.
So that's 3/2 if you get a common denominator equals 1/2 K. So what would K have to be?
3.
And then just,
And in this case, it will be positive 3 because the directrix is above the x-axis.
right, so K times E is 3 times 1/2, which is 3/2, over 1 plus 1/2 sine theta. So it looks like we need to times everything by a 2.
Right. We don't want to leave it in this form. Don't leave it in this form. You've done most of the work, but you're not done yet. So we're going to do 2 over 2 because that's a very specific one. And you get that bad boy right there.
There we go.
There's your answer.
All right, so let's do it again.
Okay, let's do it.
So this
Give
time it's
yourself
a
a rough sketch.
hyperbola.
Yep, which means that we should get now an eccentricity greater than 1. So if we have another mistake,
Well, let's not let that happen again.
then what's going to happen is we'll be able to tell based off eccentricity. I feel like those XY axes
Would you just
are
calm down? Okay, 3
crooked.
comma 0. So 0 is this way. This is 1, 2, 3.
Focus at the
And
pole.
that is the end point of its transverse axis, and then -15 comma pi. Now this is tricky. In fact, I need to move this.
Yeah, move that whole thing over. Because what we're doing is we're going around pi units and then moving 15 in the opposite direction. So basically that's like saying 0,
So
15.
we're at pi this way, but we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. What's your problem?
I was just waiting until you graphed it. You gonna stretch your not straight line all the way out there?
Absolutely.
Oh
Okay,
my.
those are our
God.
vertices. So that is where our hyperbola actually comes out each direction,
Right.
like a so.
Okay, so here's the deal. We're going to have a directrix then just to the right of the portion closest to the origin.
Right, because we've got this backward C looking thing, and then that's where our
Directrix there,
directrix
yeah.
will be. It'll be
Remember,
somewhere.
you
here.
have a focus at the pole. You have a focus at the pole
Right here.
right there.
Okay, so that means that it'll be in the form R equals KE over 1 plus E cosine.
Yep.
And let's do it the other way, the way you mentioned on the first way. Oops.
Oh my. Jeez. Okay. Sorry about that.
We're going to try this the way that Hazelwood said on the other one, where we are going to do E equals C over A.
Right.
Right? Okay.
Because these are some things that we can discover.
Yes, so and especially since this is nice and it's between 3 and 15, that
Right.
means that this is 12.
12. So
And that's 2A.
Right. So 6 units in from one side gives us A. So
A is 6.
A is 6. Well, looky
Okay?
there.
Then
So
C is the distance from the center to
to
the
the
pole,
focus,
right? The focus.
to the point. Yeah.
So
So
if
we've
A
got to
is
creep in
1,
6
2,
from that 3,
4,
which
5,
should be
6.
9, right?
Yeah. So C is
So
9.
C is 9. So now,
Bam, 9 over 6.
Yeah.
Which is
What you
3
talking about?
halves, which
That's
is bigger
right.
than 1.
that's what we needed to have.
Now, how do we find K?
Well, now here's how we find K. K is equal to E times C. What is K equal to? I can't ever remember. K is equal to...
I don't think there is one.
Oh, is there not a thing for...
So
finding-
now let's pick a point
Son
and
of
plug in.
All right.
So 3 equals, but now we can put the 3 halves in here, and it'll
Right, 'cause
make
we know
it
what's
a
going
little
on.
uglier initially, but
Cleans
in the
up pretty
long
nice.
run, it'll be okay. 0. Cosine of 0 is 1.
Right.
So that's just going to go away. So on the bottom, we have 1 plus 3 halves. So this is 3 equals... We could just get rid of the fraction, like the 3 halves, if we
Yeah.
wanted to multiply by 2
Right,
on the
multiply
top
by
and the
2 on
bottom.
top and bottom.
So that's 3k equals
2
2
plus
plus
3.
3, which is 5. So multiply the 5 over, that gives you 15 equals 3k. So k equals 5.
Now, on both of these, we had to actually use a point we knew to help us find the information we didn't know.
Right.
On the example 4, we used the R value. On example 5, we used the theta. So you choose the way that you feel most comfortable with.
Right, so 5 times 3 halves on top is 15 halves.
15 halves.
Over 1 plus 3 halves cosine theta.
Multiply everything by a 2.
My thetas are really not going so
Yeah,
well.
your theta's to death. Looks like a peace sign.
Okay. 2 plus 3 cosine theta.
There you go.
There it is.
Enjoy, children.
Example 6. Now, there's this formula. Maybe you should add it to your graphic organizer in this section. My bad.
You're bad, all right.
Yeah.
Now, you might notice that in every, basically, section of conics that we've dealt with, except parabolas, we've talked about solar system-y stuff.
Yeah, it's a very, very realistic thing. So this has to do with ellipses with an eccentricity E and a semi-major axis A. And so
This
it
helps you
looks
with
similar to...
Orbits of planets, basically, is what it helps us with.
Right, and it should look similar to the A equation that we've been dealing with, but we basically rewrote K times E up here on the top as something
A little
that the
different.
book helped us out with.
Right.
Now, they gave us, in this example, they gave us a whole chart, but we're just concerned on this with Mercury, and we want to use it to approximate its aphelion, and perihelion distances to the sun.
That would be closest and furthest.
Yes, so E and A, that's what they gave us, because E is eccentricity, A is our semi-major axis.
Right.
And so in order to figure out the max distance and the min distance, I don't know, what do you think we should do?
Well, we got A. Do we need to have B at all? What are we trying to find? We need to find C. So if we know what the eccentricity is and we know what A is, do we know if we're working with an ellipse?
I have a better idea.
Okay.
Okay, so we're gonna plug in E and A into this formula, right?
Okay.
And here's what's gonna happen with our graphs. So this is, I drew that the wrong direction, kind of. Like, this is our ellipse situation that we've got going on.
Right.
And so the closest that it should be, if this is our focus, the closest it should be is right here.
Right.
When we're at something comma 0.
Ooh.
And the
that's good
farthest
thinking.
is r comma pi. And so we're going to plug into this formula. Why'd I make that face? I'm still on camera. Okay, let's just keep going. And I'm going to leave it as cosine theta right now, because here's what we're going to do is we're going to plug in 0 and find out what the closest distance is. We're going to plug in pi and find out what the farthest distance is. So if I make theta be 0, so in my calculator, if I have the capability to make fractions, then that's helpful.
So basically you picked a value that we knew to plug in.
Yeah.
Okay, that's a good job.
0.2056
Right.
squared. All right, that's the top. And then on bottom, 1 plus 0.2056. And then where theta is, I'm going to put 0. Make sure you're in radian mode.
Yeah, you want to be in
Actually,
radian
it won't
mode.
matter for this one because 0 is 0 is 0, you know?
Or 1.
All right, so this is 45.996, and this is in gigameters, I believe. The best kind of meters, if you ask me. That is the closest, which is the aphelion. Never heard these words before this book. I wonder if they made them up or if these are legit.
We'll have to tweet this to an astronomer and see what they say.
I don't know any astronomers.
Well, we'll just hashtag it astronomers.
Now let's plug in pi.
Which is going to be the same sort of situation.
Yeah, except that we'll put
Except
pi.
now
So
it's
I'm
gonna
just
be
going
pi.
to scroll up on my calculator and put a pi where 0 is. And get 69 sub 0.804 gigameters.
Hi.
And that's the perihelion.
That's the furthest from.
That is. Ooh.
Wow, that was easier than I thought it was going to be. We just had to plug in a thing.
Yeah. So code word.
Oh.
Are you ready?
20, 20, 40.
Okay.
All right.
Here's your code word. It's right here.
Wow, at the very end.
Very end.
We're mean.